Erico Mattos is he worked for Soli Organic. It's a big vertical farming that uses soil. But I actually contacted him because I saw a very nice talk on greenhouse lighting and adaptive lighting, and I was really impressed. He was working formerly for GLASE, which is the greenhouse lighting and system engineering. So he's going to present some work from both his previous work and his current work. So welcome, Ericos, and thank you.
Thank you so much. Hello, everyone. Good morning. Thanks, everybody, for being here. Deborah, thanks for all the work in the morning.
Sorry for get rid of that thing.
And I don't think the speaker.
I don't think people see that. Nobody can see that. Yes, that's you're talking about the.
Peter, can you get rid of the ribbon?
There you go.
And I don't think can they hear me? Can you hear me on the back? All right.
Speaker for the. Okay.
Yeah, I can hear you.
All right. Thank you, Brett.
Thank you.
So good morning, everyone. Thanks for being here. Thanks for all the effort to get us inside the building this morning. We are here, and that's fantastic. So like Deborah said, my name is Erico Mattos. I work for Soli Organic today, which is just a second. There you go. So Soli Organic is the largest producer of organic herbs and leafy greens indoors, headquartered in Virginia, Harrisonburg, Virginia. We have factories everywhere across the United States. But before this work, and I joined here about a year ago, I used to be the executive director of GLASE, Greenhouse Lighting and Systems Engineering Consortium, where I worked was a public-private consortium, work with lighting companies, greenhouse growers, vertical farmers, mainly focused on lighting, but other systems as well, ventilation, airflow, irrigation, building designs, a lot of things that Carla covered this morning. So it was great having Carla going first. She covered a lot of the things. I will really be focusing on lighting today. And since I've never worked with citrus, what I thought about here was to identify a few things that we learned from the lighting in the CEA world, controlled environmental agricultural world with leafy greens and herbs and potted plants, and find a few parallels with the citrus industry. So I don't have answer for you guys because I don't know anything about specifics about citrus, but there are things that we can point out, how we can identify places, and we can work. There are a few tools that then we can use to go after the solutions you might be looking for. So we'll provide an introduction on those, and we can go back and we can talk more in details over lunch, or if you want to learn more about, just follow up with me by email later, and we can go after specifics. So to start, why normally people use supplemental lighting for crop production? This is a picture of a very large greenhouse named Revolution Farms in Michigan. In Michigan, I think everybody knows, is not the best weather in the United States. They're close to the lake. So you can see the sky over there, pretty cloudy. And you can really set back production, right? That's a 24/7, 365 leafy green producer. And they need to have the consistent quality. They have to have the production on time every day. So normally, supplemental lighting in greenhouses is used to maintain adequate light levels. And you can make up for the daily variations. So you can have a day that is sunny in the day, cloudy in the afternoon, and clear back again, or whatever the weather is, it goes up and down, the fluctuation of the sun. You have the fluctuation of the seasons of the year. You don't use lighting on the summer normally, so that's not here. And northern latitudes, we're gonna have to use lighting no matter what. Another application I think Carla covers a lot this morning is the indoor farms. In indoor farms, they have 100% artificial lighting, so it's not supplemental lighting, it's 100%. And you've been seeing the advances of LEDs in that field pretty strongly by the efficiency of the fixtures. You get more light by the energy that you get inside the fixtures. For the growers, the benefits, they're going to be able to maintain the production quality year-round, and they can reduce the production time as well. So if you go back here to the example in Michigan, it's not that you cannot grow lettuce. You'll be able to grow lettuce, but it might take 2 to 3 months, a crop that you can grow in 20 to 30 days. So that's why you need the supplemental lighting to keep on top. When you think about lighting in the CEA industry, there is 3 main aspects of lighting. And I'm very glad that Carla covers a lot the light spectrum, the color of lights. I'm not going to talk about this here. I'm going to talk about the other 2. This is a nice slide from Eric Runkel. He's a professor at Michigan State University, and I love the little diagram that he makes, pretty easy to understand. So you have the light quantity, is the amount of light we are providing to the crops. You have the light spectrum, which is the light quality, the colors, and photoperiod is the duration. So it's how many hours in a day the plants can perceive lights. Plants have photoreceptors. They know when there is light, when there is no light. And this is important because light quality is mainly related to the quality of the crops. So you can think about morphology, you can stretch the plants, you can change the colors. There is a lot of qualitative aspects that come with the light colors. When you think about plant biomass, it's the photosynthesis that is powering the crops. And light quantity is really important here, is the photosynthetic photon flux that we saw, and the DLI, the daylight integral. And the photoperiod can help short and long day plants to flower or not. So they have those cues from nature and they know it's time to flower. So very important to manipulate flower in the ornamental industry. And as I learned in the citrus industry, we can take advantage of the photoperiod as well. So some basics of the lighting before we go into the examples. So when you think about light spectrum, Carla showed us that is the spectrum of light from the sun that you see here. So it goes from about 250 nanometers all the way to 2000 nanometers. That's the wavelength. But what the plants perceive, coincidentally, is the same waveband that we see as the colors. So we are in that 400 to 700 waveband, and that's where the plants perceive light. We call photosynthetic active radiation, PAR. Traditionally has been measured from 400 to 700 nanometers, which is exactly the visible light. And this is about 50% of the light spectrum from the sun. Now, most recently, some researchers named Bruce Bugby from Utah University, Mark Van Eersel from University of Georgia, and Shuyang Zhen from Texas A&M, they have proposed extended photosynthetic active radiation, we call EPAR. So they found that photons that are on the far red, so if you see there on that image, by the way, I just overlap, well, not me, I got the image from the internet, where overlaps our eye sensitivity to the colors, which is the same as the plants perceive. So that wavelength from 400 to 700. But now the photons at 7 to 750 can also induce photosynthesis. They have published very nice papers here. I'm not going to present their data, but there is evidence that they can induce photosynthesis as well. So now people are using the extended photosynthetic active radiation, which now goes from 4 to 750. When we think about measuring this, and that's important because when you're measuring light, now you have to account for those extra photons. And that's how we're going to go back to the same diagram that Carla presented, how you measure light. For the presentation moving forward, I'm going to call PAR, photosynthetic active radiation. I'm not going to use the EPAR because it's confusing. All the way up to a year and a half, 2 years ago, everybody just used PAR. Now we're using the EPAR. So let's just stick with the PAR for this presentation, and you can compare data with the past as well. When we measure light, you can think about the number of photons. So that's what we're measuring. Deborah, I think you asked about the colors for Carla. For the plants, a photon is a photon. Once it's absorbed, it will induce photosynthesis. They have different absorption rates, and then one will be better than the other. But once it's absorbed, it kicks the photosynthetic process. So the way we measure light, we are counting the number of photons that fall in a certain area per second. And that's how we call the PPFD. Now we have the flux density because it's per area per second. And this is calculated or measured in micromoles per meter square per second. When you think about the daily light integral, and that's an instantaneous measurement, the daily light integral is the total amount of light that the crops see in a certain amount of time, in 24 hours. You might not be giving the crop light 24 hours. So you calculate by the hours within 24 hours that you provide light for this crop. You integrate all this light, and now you express this in moles per meter square per day. That's an easy analogy that I use in other industries before. If you think about PPFD with a rain analogy, if it's raining, it's how much is raining right now. It could be pouring, it could be drizzling, it could be a little bit. So when you take those PPFD measurements using a light sensor, which we call the PAR sensor, you're going to be getting that instantaneous amount of light coming. When you think about the DLI, the analogy with the rain is how much water you get throughout the whole time that it was raining. So you can have the little cup that will tell us in millimeters is the same analogy for DLI and PPFD. My last one on the basics of lighting, the light sensor itself. So here is the PAR meter. That's a quantum sensor, so measures the number of photons. That's very important when you compare about a lux sensor. A lot of people use lux sensors to measure light, which is for visible light. You should not use this for plants because those sensors, they're weighed just like the picture that I showed before with the human eye. Because they're calibrated for the human vision, they will count green photons with a higher weight instead of every photon like the plants see. So in this case, with a PAR sensor, you can see the PAR range is the solid teal line. So it's a perfect square that goes from 4 to 700 nanometers. And this little sensor here, this PAR sensor, the sensitivity per photon is the green line. So you see that it's very proxy to what the plants are seeing. Now they're selling EPAR sensors that extended photosynthetic active radiation. So it'd be similar, but that little square now would go all the way to 750. So just think about these are looking for sensors. You definitely need to use a PAR sensor, not a lumens or foot candles or anything like that. And you have to understand if it's a PAR or EPAR, so then you can account for the correct amount of light they're measuring for your crops. So changing gears now that I know a little bit about the basics of lighting, is supplemental lighting good for me or not? So that's the question that normally people in the CEA industry will ask. Do I need a supplemental lighting for my production? Well, those are three easy questions you have to ask yourself to come to this conclusion. How much light does my crop need? So here I'm talking about DLI, the amount of light. So do I need 17 moles of light a day, 20 moles of light a day? We're going to see a few examples. Once you know the amount of light that your crop needs, the next question is, how much light do I have available throughout the year on my location? We're in Riverside. There's a lot of light here. But if you go back to Michigan or upstate New York, where I lived for 5 years, it is not the same thing. There's much less light over there. After you know these two aspects, you're going to do the difference and you know what is your supplemental lighting needs. You're going to know how much light you should provide to your crop to achieve that consistent production throughout the year. This is normally what we do for leafy greens, potted plants, fruits. Now, I'm entering new territory for me here, and I was just doing some research for this presentation. I started to look for citrus production in nursery, right? We're not going to put lights in the field, but in the nursery, we can speed that process. So looking at that, I found 4 aspects. I'm not saying that's right or wrong. Those are 4 that I identify. We could apply here. It could be more. It could be less. We can discuss this throughout the presentation. But I saw that when you're producing the plants the citrus plants in the nursery, you have the rootstock production, in which you want to accelerate this process if you're in a controlled environment or agriculture. You have the places where you keep your mother plants in greenhouses as well, in controlled environment. You have the bud grafting, so where you're getting the grafts to make your new plant, and then the side development. After you do the grafting, you're going to keep those plants in a controlled environment for a few more months until the plant's ready to reach the field time. So those 4 aspects, I believe you could benefit by supplemental lighting. I'm not saying you have to go through the calculations to see if it's good for you or not, but those could be areas that could potentially be beneficial. And within those 4 stages, there are 3 aspects of lighting that we can look a little bit today. The DLI, which is the total amount of light, and they're going to help your plants develop biomass, so establish the root production, the leaves, and just get established. There is the photo period, which is the hours of light that the plant is going to be perceiving a day. It's not about the quantity, it's more about sensing light. So there are nice applications here. You can control the photo period without a massive lighting system, which are expensive. And then the spectrum of light. I'm not going to go to the spectrum. The spectrum is complicated enough in the leafy greens and the areas that I'm familiar with. Not knowing the citrus industry, I'm not going to get here, but I'm sure there are things this group is going to find out in the next few years, if not already finding out. So again, after a little bit of research and ask some people around in the room here, it is hard to find exactly what is the amount of light that the citrus crops need. The table here, all the other crops, I know they come from Hort Americas, which is the company we just saw from Carla. So they do extensive research. They have very good numbers. Now for citrus, we didn't really know. I took this in after doing some research, and it seems that between 16 and 20 moles of light a day, you can get a good amount of light for your crop development within the controlled environmental greenhouses. Now, going back to my 3 questions, right? How much light my crop need? That's the first one. So I'll take 18 for the sake of this exercise here. Once you know how much light your crop needs, let's see how much light you have in your location. This is a nice tool that I encourage everyone here interested in lighting to go and visit. They call DLI Maps, and that is published by Jim Faust from Clemson University. If you go to this website, you can insert your location, and that will tell you the average amount of light that is available at that location throughout the year. So you go there and you do January, February, March with your location, it will tell you. So you can see here the different amount of light within the little legend there. So you go all the way from 5 to 10 moles of light in a month, all the way to 50 to 60 moles of light. Of course, you're having northern areas, less light, southern areas, more light. So using that map and knowing how much light we need, I prepared this for this presentation. So I went to that website, I put the zip code of Riverside, California, where we are. I got the target amount of light for citrus plants, 18 moles of light per meter square per day. And I put this on a table to calculate, do we need lighting or not? So the first column, we have the months of the year. I skip the summer. So you start August, September, October, November, December, January, February, March, April. Then from the website, the DLI calculator, I found how much light is available outside of the greenhouse, not inside. So that's how much light you would measure outside of greenhouse. I am assuming a greenhouse lighting transmission of 60%. The numbers vary widely here. If you think about a new glass greenhouse, it can be up to 90, 95%. Poly, nobody already that much. A new poly would be, I don't know, maybe 80%, but most of the greenhouses that you see are not that. Most of them are 60, 50. So by doing this calculation, now you know how much light is available for your crops inside the greenhouse throughout the months of the year. And then you know your target, right? Just by subtracting one from another, what you found here. If you are in Versailles and if you have working with those conditions, you don't need supplemental light in August, September, and October. Now you need supplemental light in November, December, January, February, and then you don't need any more in March and April if you want to maintain 18 moles of light per day. Now, one interesting thing to see here, if you're going to design a lighting system, and you're going to go into the details later, normally you don't go for the maximum amount of lighting that you need. You're not going to design a lighting system for the darkest day of the year, right? Because you're going to be paying too much. So you can say, I'm going to achieve 90% of my needs or 95%. But for the exercise, let's go with the 4.5 that you're going to need in December and January. Once you know how much light you need, you have to think about lighting design. So Carla talked a little bit about that. Now you know the DLI. Knowing how the DLI, which is the 4.5 moles of light per day, you have to think about how many lights I need, how I should displace them in my greenhouse, so I can get to that amount of light within a certain amount of time. That's an example I got out of the internet. It's just a light map. We're going to see more detailed numbers in a second. But the way the companies do normally, they will place the red lines indicate the LED light bars, or could be an HPS light. You pick the technology you want to work with. And then you do the mapping. So you go ahead measuring under the canopy, above the canopy under the lights. And in this case, they're shooting for 80 micromoles all around. And you see on the right below the lights, you might have 100 micromoles. After doing that, there are custom design, software designs to do this. The lighting companies will work on this with you. You get a light map. It's something like this. So in this case, you can see you want to shoot for consistent lighting across the canopy. So in this case, the red zone here, you're going to have a higher light intensity. As you go around, because I have several lights overlapping, as you go around, it decays a little bit. So you want to keep a good consistency. You're shooting for 85 to 95% consistency. It's hard to do that, but that's a good number to aim for at least. All right, going back to our example, right? You want to provide 4.5 moles of light with your supplemental lighting system. Now, one trade-off to consider. When you're looking for light, this table here is showing us the hours of lighting per day. So that'll be how many hours you can run your lighting system in a day. And here you have your light intensity. So what is the maximum amount of light intensity that your crop's going to receive when you have the lighting at full power? There are different ways you can get, different combinations, and that makes sense. If you have a more powerful lighting system, you run for a few hours, you get to the number that you want. If you have a less powerful lighting system and you run for more hours in a day, so you're going from 8 hours all the way to 20 hours to be able to get to the closest 4.5 moles of light in a day. The big trade-off here is, can your crop be illuminated for 20 hours? If you think about short or long day plants, some plants cannot. They need some break. They need dark time. So sometimes you cannot, and then you eliminate those possibilities here with a low intensity system. As you move to less hours, to compensate, you have to have a more powerful lighting system. The trade-off here is money. So if you think about a lighting system that gives you 150 micromoles light intensity at canopy, you probably need twice the amount of lights that will give you 70 micromoles. So you're getting the twice amount of lights, you're getting the twice amount of light in your canopy, but you're paying for that installation. So all of those things must be taken in consideration. What is your target, how many hours your crop can receive, and how much money you want to invest. And even when you get to this and you find what is your ideal situation here, you have to think about the lighting itself. It's HPS. It's much cheaper, but it consumes more energy, has a lower lifespan. You want a LED lighting, more expensive, but it lasts long, less operational costs because you use less energy. So you're gonna have to consider all those different factors. This is for the amount of light. Now I'm gonna talk a little bit about photo period, which is the hours that your plant perceive light in a day. Using another available tool on the internet, which is the daylight hours, and I'll share this presentation. So if you want these links, you can get all of them. You can find exactly how many hours of light it is in your location. So I did the same thing. I went there, I put the zip code for Riverside, and I could find in a day how many hours of light you have. They break down into pre and after dawn, which I didn't get. There's very little light in the morning and the end of the day. And then they give you the exact number of hours that you have a certain amount of light. They have a threshold, I can't remember right now. But it will be the similar thing in your greenhouse. Your beginning of the day and end of the day, you don't even get the light through the angle. So I took the chunk, which is about 90% of the light hours in a day. And I populate this little map here. So same thing, we're gonna August to April. I look, and the audience can help me here. I found that when you're doing the citrus production in nursery, there is a benefit in extending the day hours. So when it's dark, if you provide a little bit more hours to your crop, they're gonna perform better. It is common to say, what is a short day, a long day crop? 12 hours. So if you have more than 12 hours of light, you can say you're going to the long days. So I just set a target for 13 hours of light in a day. That is my criteria. We can change. You can do whatever you want with those tools. So that's the target, is to provide the crops 13 hours of light per day throughout the months of the year, excluding summer. This is how much light you actually have in Riverside according to the website. So I did a little bit of visual here, but here I'm breaking down by the full hours. This is the actual number that the website will give you, so it's very precise. And when you do the math here, you know that in August, you don't need supplemental lighting. You're already 13 or higher. As you go September all the way to April, pretty much, you're gonna need some supplemental lighting if you wanna get a long day exposure to your crop. The cool thing about here, I'm not gonna go into the costs here, because when you think about day length extension, all you need is a little bit of light. It's very minimal. You don't need much. So to give an idea, we're talking about the calculations that we looked there for the DLI of 4.5. You're thinking about 70 to 150 micromoles light intensity that you need for the supplemental lighting system. For day length extension, you can go as low as 10 micromoles. So the incandescent bulbs will do the job. So that's the cool thing here. You don't need, this is not expensive to do if you think about extending the photo period only. But here you know when you would need a system to provide. Going from one slide to another, as I populate, you can see the little squares at the screen. So that all looks like visually. You provide the day length extension, you get to the 13 hours of light a day, and hopefully you can get the benefits they're looking for in citrus production in nursery and greenhouses. I'm gonna change gears now. Before I change gears, any questions about this? Is there anything? Was everything clear about the concepts of DLI, photo period? Yes.
One question. On the daylight extension, because it doesn't have to be very much light, does the quality of the light matter?
Can you repeat the question for the people online?
Yes, perfect. So the question was for the photo period daylight extension, because the quantity of light doesn't matter, does the quality of light matters? Is this the question, the color of light? Not really. No, you can do. It is a phytochrome process that you're triggering. So if we stick with the light within the visible spectrum, which is pretty much every light, don't get weird. Pretty much, don't go with a very far red or very UV. Any light with the visible spectrum, incandescent, HPS, metal highlight, LEDs will do the job. So it's minimum importance, almost negligible.
Supposed to be a workshop, an exchange of ideas. Don't be, especially for citrus, we don't know anything. So the numbers you see here are not set in stone. Just an example. Mark, yeah, go ahead.
Yeah, I manage the Texas Citrus Budwood program, and thought about lighting before and if it could be beneficial to our program. Um, it's very interesting. I would like to know, are there companies or people that we can talk to that could come in, because I'm not an engineer, and take a look at our specific situation, the way things grow there, our structures, and set us up with a program?
Absolutely. Yeah, absolutely. Every lighting company will do that for you. So you can bring them at the door, and I can provide you 10 names from big brands to small local brands, but part of their business model is to come, understand your needs. So they're going to look at those, how much light you have, what is the target, and so on. And they will help with the design, how many lights you need, how to place the lights, the lighting control options that you have, when to run. They go further along. They go and they help, because light is expensive. They normally go and talk to your local utility company and they try to get rebates. So if you do LED installation, it's more expensive, but it's more economic in terms of operations, right? So they can help you to get rebates through the USDA, local utility companies. There's a wide range of support programs. Absolutely, yes.
Because our program is somewhat different, although it's modeled after California. It's somewhat different because of the conditions there in Texas. And so we're a little bit unique, and our objectives for our industry are grafting, regrowth, supplying germplasm to the industry, and so anything that can help speed up or efficient and make that process more efficient, what we were looking for.
I'm going to talk about.
Oh, good.
I'm going to show you. Yeah. Okay.
Absolutely, yeah. I think working with the academics as they unveil the benefits of lighting, because really you have to quantify, right? Like George said, those numbers, they're all simulations. I don't have any numbers on citrus, but as the academics go down and quantify the benefits, that will help you now to make the decision: is that worth or not? I'm sure you're going to see benefits. It does not go backwards. You will get more production, less time. The question is it worth the investment, right? But yes, it's exciting having a brand new industry looking into that. It's super exciting, super exciting.
One more question. We actually got like a quote to do supplemental lighting in our nursery, but the main problem was the power. Like it requires so much power to raise. But the other thing is that like in the calculations that you were doing and in the vendors that we talked to about the supplemental lighting, no one really had any answer on, because of course, like in a greenhouse, right? Like you're going to be blocking out like the natural light by putting lights in there, even if they are slotted. So like in some of the lights that we were looking at, it would have basically been like covering 50% of the area. So like how would that be accounted for in like a calculation like where, you know, because you're going to need additional light to cover for the daylight that it's not actually giving.
If you get to a point that you're blocking 50% of the natural sunlight, I can tell you it's not worth, for sure. But yeah, absolutely. But there are ways around this. I can send you more contacts to look around. I hardly see that happening, but I understand what you're saying. Makes sense. So there's a few things. Cornell University has a very nice tool, a software tool that does project the shading from the structures, and you can mount there not only the lights, but the entire greenhouse structure as the sun goes by. They can account for, calculate, know where it is throughout the day. So there's tools on that side, the modeling side. But on the design side, most of the lighting manufacturers, they have lights designed for greenhouse and lights designed for vertical farms. Vertical farms, they don't care about blocking because it's inside anyway. But the greenhouse lights, normally the shape and form of them, they're long tubes like this, which is supposed to be mounted on the truss.
And then it had like gaps, and then it had like, I think it was like 8, like 2
bars, yeah. This is not my opinion. I don't think that's the best design for greenhouse. The best ones are the sling. Carla showed one of them.
I saw
that type of light, because they're meant to be mounted on the greenhouse trusses, on the greenhouse structure to begin with. Yeah, we can look for more. There are alternatives, but you're right. If you're blocking 50%, don't go with that. Absolutely, yeah. All right, let me show you. Yeah, one more. This part's pretty cool. So this project calls Project LAMP. It's a USDA sponsored project. It's one of those multi-million-dollar projects that they got. It is led by University of Georgia by Professor Mark Van Eersel, who passed away last year. But then Ronito Ferraresi, the first one on the top left, is leading. Is a bunch of people. That's what I mentioned here. I don't have to go through all of them, but it's a collaboration with several universities, USDA, and great people, great quality. Cornell is one of them, so they have those tools that I mentioned, and they develop two lighting calculators, which are pretty cool. So let me go see if I can do this smooth here. I have to find. No, that's not right. I mean, the browser. I have this open, and it can do a nice. Okay. So lighting calculator, there's two tools here which are pretty cool. One of them is if you have a lighting system in place already, let's say your greenhouse already has a lighting system, and you want to know with that lighting system, are you getting to the target that you need? After knowing how much light you need, what is the DLI that I have to provide, you can come here and you calculate throughout the year based on environmental conditions and the lighting system that you have, will tell you, all right, with this system, you're going to be able to get your target 80% of the time in the year, or 90%, 100%. That's for existing ones. I'm going to focus on the second one, which is if you were to come up with a new lighting system, so her case, for example, you put here all the specifications. I will tell you based on that how many days of the year you will get your target, and to your point, then you can know the benefits that you're going to get throughout the year by installing a supplemental lighting system. Let's go in here. I did this on my computer a few times. I had everything saved for Riverside. I don't have now. I'm going to need the zip code. I don't have top of my head. If we know the zip code would be fantastic. So this is the tool. I'll share the link with everybody. It's a publicly available tool, right? And pretty much here, we're going to add the location of the greenhouse. The first
So let's do a zip code in the valley because no, but we don't want. There's not that many absolutely. What's your zip code in one?
93221.
Because the agriculture moved out of here sometime ago. Most.
So we have here, I'm naming the greenhouse University of California, Riverside. We got the zip code from this specific location. Electricity rate, if you get to know, great. Otherwise, I'll do 25 cents. That's what I Google for Riverside. 25 cents kilowatt hour. Sounds right? Too high, too low.
At home is much cheaper than that in Riverside. I don't know, do you get special rates in farm operations? You know how much? Make it 15. It is expensive or inexpensive? Okay, make it 20.
20 cents kilowatt hour. All right. Save this one. All right. It tells us we're good. We're moving to the next step. So we're going to talk about the greenhouse design. Here we're going to say the design name. So we can do it's the University of California, Riverside. It is a poly glass. What do you want to hear for the greenhouse?
Twin wall.
About an acre is okay. All right. Transmission. So if it's poly, what do you want to do? 60, 50, 60, 60% transmission. Target DLI. Can I do the 18?
Yeah.
That's where it's important to do the research. So that'll be the efficacy of the light system. Just a few facts here. The DLC, Design Lighting Consortium, it gives rebates for lights that have a minimum efficacy. And here is how much light you get per joule of energy. So basically, how much energy you get and how much light it's producing. Good LEDs today, they're going to go up to 3.5, almost 4. You have to use, especially in California, I believe, it needs to be higher than 2.1. And that's the threshold to get high pressure sodium out of the options here. So I'm going to do a median one. I would say 2.5 micromoles per joule.
Can you try the one we have? It's a 3 point.
I have a 3 point something. Oh, absolutely. 3.2. Yes, absolutely. 3.2. Now that's an important one. So percentage of the days where you reach your target DLI. That goes back to my point. You don't want to design a lighting system to get your target on the darkest day of the year because there's going to be too much installed capacity to be used 1 or 2 days. So what do you want to do? Maybe 90% of the time, 95, 85, I'll do 90. So 90% of the days you'll get to the target. And that really helps with the design, how much you're going to spend money for your light system. Hour zone, that's an important one. That related to the photo period. When I did my calculations, I said you could use the lighting system for 12 hours. It doesn't mean you will. Is that during the day, during the nighttime? You have a number in mind?
Traditionally, in the book and in everyday language, we call the citrus as 16:8, right?
Okay, 16 photo period. Perfect. Excellent.
That's what we've been educated.
Perfect. What this number for this case here on this tool, what this number gonna mean is related to the DLI, is the amount of light. Not really, it will do the photo period because that's what the tradition, the light's gonna be on for 16. But the longer you run, more time you're gonna be illuminating the crop. So higher gonna be the DLI with the same install capacity. So that's why this number is important. But then it's gonna be more expensive, the operation as well, because you're running the lights longer. But you can go back and play as much as you want. All right, the demand charge, we need a number here. Don't worry about it. I don't know if you're familiar with this. The main charge is if you exceed a certain peak of energy in a month, you get the demand charge costs. And that's very expensive because now your entire energy bill is based on that 1 second that you got to the peak. So you have to be careful here. And California is well known for those costs. So this is not gonna change everything, anything at the end. There's a separate section for this. So put $5 per kilowatt hour if you reach this. We have to populate the field. And I'm happy to talk more about these. If you want more details about that, you can go back. All right, now that I have everything that we need, the system, by the way, this is the monthly area lighting. Here's assuming that you're using 100% of a greenhouse for citrus production whole year, right? Because if you think about the ornamental industry, is different. They're gonna use pots here, but then they move. So that's why the calculation didn't take into account the use capacity of the greenhouse. In this case, you're just using year long. And after come here, you hit the update button and you see the numbers. So those are cool graphics here. So first of all, what we see, how do we do zoom? Sorry, I never use Windows anymore. How do I do the zoom? I just, I found, okay, perfect. All right, okay. So what we're seeing here, based on the specifications that we enter, 60% transmission, target DLI 18, and so on. I'm not gonna repeat all of them. With those maps here, this is the number of days, sorry, that's the DLI available. So based on natural conditions, that's why the zip code was important. So the zip code went to the DLI maps and they got all this historical information. Naturally, you would get those days of the year, you're getting to the target DLI that you want, which you see the line at 18 here. That's our target. So naturally, you're gonna be achieving from what? What is this here? You are February, all the way to November, you can get your target DLI. On these other days of the year, you're not gonna get there. Now, when you use the supplemental lighting, now you're gonna be achieving your target DLI much more often than before. So now those are just the days of the year you're not gonna be targeting the DLI because they are above that 90%, right? So you're not gonna design a lighting capacity to do this, but you're gonna be achieving the target DLI all those days of the year here that are not a flat line, which is the natural one, is because of the supplemental lighting control. So now you have a much better condition for your crops, right? You're removing all those dark days, you're getting the light that you need. For this specific condition, you would need to design a system that provides 146 micromoles per meter square per second. So that's when the trade-off of how many days of the year you want to achieve, what is the photo period that it can run your lights, you come up with 146, and your target amount of light, the maximum amount of light that will give you in a day is 8.35 moles of light per day. This number comes from the capacity that you have times the photo period. Carla showed how to do the equation. I'm not gonna go to math. It's a simple equation. I can show later how you go from this number to this number, but basically it's related to the number of hours that you run in the lighting system in a day. You can get a total amount of 8.38 moles of light, supplemental lighting in a day. This is very, very good news for a production, system that wants to eliminate the uncertainties and the setbacks from lighting. You can go back here, you can play back and forth as much as you want. If you do this over and over and over with the different settings, you're gonna get different graphics and you can find the place that suits your needs here. Let me go back to the presentation. because now, so we have here
According
one
to
for
this
this.
graph, if the
Yes,
it's flat lined, I'm getting 16 hours of
Yeah.
of light
yes.
naturally.
Well, no, in this case, yes, because, well, let me step back. This means you're getting to the DLI, because here's designed for the DLI, not photo period. Yeah, so you're getting to the DLI here, but because you have your system operating 16 hours a day, it will get there anyway. You're just going to provide more lighting if you need it. Because if not, this is by natural lighting, and this is with the supplemental lighting to get there. So you would get the 16 hours every day. And here is even if you were to run 16 hours of day, you would not get there. But then you stop because you put the requirement 16 hours and you put the requirement of 90% of the days of the year. So that's why it gives a lighting capacity below here. I don't know what I changed here. Must have pressed something because we changed these numbers just now. All right. Let me go back to my presentation. Okay.
For those months that the line is flat, does it mean my lights will be off? It will not be on at all?
Yes, because those are those days here. Most of those days in which you can get it from the sunlight. I don't know how to go back to my presentation now. This one?
The Deborah Pagliazza, get it out of the way. You should be able to.
Oh, yeah.
Right.
Thank you. When I've done the calculations beforehand, I saved this one just in case we need it. We changed the number, so if we could not get the connection in the internet, it's the same thing. So I put all the systems here, the settings, would get a similar graphic like we saw. In my case, because I had different settings, it's a different set of results. But one thing I would like to show, and I'm at the time here, right?
You're not. I just wanted to make it full.
In my case, when I run these calculations offline, I use the same numbers that we used to get to our initial example. So when we did the initial example, we need to get a 4.3 moles of light. Remember the table, we saw how much light was outside, the 18 moles for citrus, and we conclude that we need 4.3. When I run the simulations, because I was saying to the computer, I want to achieve my target 90% of the time, not 100%, it will come back to me with those numbers here. So that's another trade-off. That'll be a clear trade-off. Going from 90% under the situation that I built this presentation, you would need a system that gives 110 micromoles. So you can buy your installation, your lighting system installation would be cheaper if you design it to achieve your lighting target 90% of the days instead of 100% of the days. So that's the trade-off. You're gonna have 10% more time of the year when you get to the target, but you're gonna pay more for your lighting system installation. I have the 45 minutes. You want me to keep going? I can stop here. All right. So I'll talk a little bit about lighting controls. This is the adaptive lighting control system. It's a brief here. Not every company offers this. I'll just talk a little bit about the concept of an adaptive lighting control system. And then you folks can tell me if you think that will be applicable and beneficial for the citrus industry or not. So the main lighting control systems you have available today in the industry. Very basic control systems are timers. So you set your timer in the greenhouse and you say, if the tradition with the citrus industry is 16 days of light hours per day, you just set your timer. So turn on here, 16 hours turn off, and that's what the system would do. So basically, with this type of controls, it is a little bit labor intensive because you have to keep changing the timer every time through the seasons of the year. You have to go back and keep changing the time that you want, the on and off. Accuracy is very low because the light's going to come on, going to stay 16 hours per day no matter what. If it's sunny, if it's raining, if it's summer, if it's winter. The trade-off here is that you're going to be spending more energy when you don't need the lighting, and you're going to be under illuminating when the lighting is not enough. And the consistency is very low as well because your crop's going to be exposed to whatever the day is giving you pretty much. You're just adding a little bit of light on top of nature. Then you have the second type of controls. If you have a climate control system in your greenhouse, you're probably going to have something like this, the threshold control. It is a moderate amount of labor. You change less because they have a little bit of automation, but the accuracy and the consistency are medium term now. Here, basically, we're going to say is if your light outside of the greenhouse comes below a certain intensity, so if you think about PPFD, say if outside of my greenhouse is below 100 micromoles, turn my lights on, and then all the lights come on. If the threshold outside of the greenhouse is above 300 micromoles, turns the light off. So everything turns off. So you're turning the lights on and off throughout the day, but you're not tracking what is the total amount of DLI at the end of the day. You just keep turning on and off according to the real-time weather. At the end of the day, you don't really know how much light your crops got it. The last one, which is the adaptive lighting control system, with a few companies are starting to offer different versions of those now. It's a much more precise lighting control system. You have a light sensor, the PAR meter that we saw in the presentation. So not a lux meter, a PAR meter you place inside the greenhouse. So you're measuring the light that your crops are receiving, and that will be constantly measuring the light and making adjustments to your lighting system in real time. If you have an LED lighting system, now you can dim the lights. You don't have to turn everything on and everything off. So basically, if the sun is providing 80% of the light that you need, you bring your LEDs to 20%. If the sun is providing 50%, you power up your LEDs to 50%, and you can have any combination. By doing this throughout the day, you're providing just the amount of light that your crop needs, but more important is tracking the DLI. So the system is tracking. I got 1 mole of light a day, 2 moles. When it gets to the 18 or whatever the number is, it doesn't provide lighting anymore. So now you save energy when you don't need, but you maximize when you need. And you have the option to say, I can extend my photo period or not. You can keep pushing the system until you get to that. So there's different combinations that you can do. So basically, it's a better view here. Monitors the light inside the greenhouse, controls the light in real time, and that gives you the amount of light that you need. Basic illustration, you have the sensor inside the greenhouse. I apologize, I meant to change the letters by citrus. I'll do this the next time. I changed all the other slides, I forgot this one. So you come here, you start to get some shade, right? The lights start to come up a little bit stronger, even stronger when you have a lot of rain. And then as the weather starts to clear, the lights go back to the normal position, to the normal state. That's what looks like a control system that modulates the light. The adaptive part of the control is here. So you can see here, the green light is your LED's output, and the blue light's the sun. They're in different scales here. That's why the lights is much bigger. So the sun is in micromoles. Normally, a very sunny day, you'd get about 2,500 micromoles per meter square per day, just to give an idea. This is one of the systems in Michigan. Oh, sorry, this one is in Buffalo, New York. So that day, you see the maximum of light that they got was about 250 micromoles, very little light outside. But this is the sun. It goes up and down throughout the day. You see, it starts here about, what is that? That should be about 8 a.m. And you get less light at about 7 p.m. And the output of the LED light is in percentage. So that's why I have 100%. When it's dark outside, the sun comes in, you provide less light, the sun goes out, you provide more light. But it keeps fluctuating in real time to the sun. And down below here, you would be tracking how much light's coming from the LEDs, is the green portion, how much is coming from the sun, the blue portion. And the goal is to achieve the target. For this grower, the target was 14. So keep monitoring, well, not you, which is the cool thing. The system keeps monitoring everything. You're busy growing your plants, and that's the point. So you're gonna think about other things, and the system takes this for you and make sure you get the same amount of light every day, saving as much energy as you can every day. That's a picture, and that was super cool. That same day that I went there and I got this information, this was in the morning. I think it was about 9, 10 a.m., and this was 3 in the afternoon. So you see, it could be a very sunny day in the morning, everything is good. But if that happens and you don't have control, your lights might be off during the entire day. You're going to be under the target, and that means your crop's going to take forever to grow. So that's very nice to have the fluctuation here. This is what looks like throughout the year. Actually less, because I got here, the data is from October to December. And what you can see here, don't worry about the numbers. What I want to show here is the flexibility of the system. Blue bar is the sunlight, and green is the supplemental lighting. So you can see, if you look just the supplemental lighting, this is the maximum, the red light. Hardly any day of the year they use the maximum supplemental lighting that they need. What that means is energy savings. If they were with any other the other two types of system, with the on-off or the threshold, they would be using much more energy. With this one, you're providing just what your crop needs. This means energy savings every time you're not touching the red light. And up here means consistency, because this is the target DLI for them, was about 14. And you combine sun plus supplemental lighting, you right at the target. Another cool thing that you notice, you see here at the initial days, they exceed even with supplemental lighting a little bit. And that was happening because when the system comes on early in the morning, is everything dark. So the system doesn't know what's going to happen. It starts to provide supplemental lighting, but then the sun comes up, the supplemental light is shut off, but then there's more sun that you need in a day and ends up catching up here. Because of that, as we notice this, the grower went there and changed the start of the photo period. So it said to the system, instead of start providing lighting at 7 a.m., wait until 9 a.m. Because at that time, the sun is there, and then it can start to react to the sun in real time. So by making this little adjustment, you see he never more provide more lighting that he needed. So super cool system. Some of the climate control companies have versions of those. Ask them about that, because you can really get good benefits. It's a simple solution, works really well, saves you energy, and gives the consistency you want for your crops. Those are some of the aspects that you can control. That will be my last slide. With an adaptive lighting control system, especially LEDs gives more control. You can do this with the HPS as well, but the LEDs gives more control. So you can adjust your photo period. Here's one way we just saw you can get energy savings by setting the system to start later in the day. And normally going to do this, you follow the seasons of the year. During the winter time, sometimes you're just going to run your system at a full power because there is not enough light. And you might not even get to the target because the system is not powerful enough. But as you go to the shoulder months, then you can start to get benefits by changing the on and off time. The day length extension, so that's a good point to your question, which type of lighting system? Anyone can do that. You can use incandescent lamps if you're going to do just photo period and day length extension or night interruption as well. But if you have a lighting system that you're using to provide the DLI, the amount of light, it's a more powerful, robust system. If you want to do day length extension, let's say your system turns off the 16 hours that Giorgio said, the 16 hours of light that you need. Let's say you get your DLI at 14 hours, not 16 hours. So that's 2 extra hours that you want to keep the lights on to get the photo period that you need for a plant, the day length extension. You don't have to run the system at 100%, at 140 micromoles. That's money. You can bring your light down to 10% or 5%, whatever is the minimum amount of light that your lights can be on. So you're going to get to the photo period, you're going to get the day length extension, but you're going to use 90% less energy than if you just keep the lights on all the time. The threshold control, this is interesting as well. We talked a little bit about this, Deborah, before. Once the industry knows what is the light saturation for citrus, it could be 600 micromoles, whatever the number is, right? So the light saturation, very basic terms here. You can keep giving light to your crop, and they will photosynthesize more and more. If you go from 0 to 100 micromoles, 200, it keeps going. But there is a point that there is a plateau that you saturate the photosynthetic apparatus. So it doesn't matter. You can go from 1,000 micromoles to 2,000 micromoles. The plant's not going to photosynthesize better. It's going to be the minimum returns. And at some point, you damage your crops. If you're thinking about the sun, that's okay. It's free. Who cares? If you think about lighting, if you're providing supplemental lighting, you pay money there. You don't want to waste money, dollars on this. So if you put a threshold control, the system will say, doesn't matter where I am on my target DLI, because the system is trying to get to the target DLI. And I'll give you a good scenario. Let's say in the morning, it's very cloudy. So you don't get the amount of light that you need. You're behind on the amount of light that you need per hour to get to the target DLI. But then in the afternoon, it's very sunny. So now the system is thinking, to make back what I lost in the morning, I need very high light levels. Now these last 4 hours of the day within that 16 hours photo period, right? That means I might need 1,000 micromoles, 2,000 micromoles. But if the sun is already giving 800 micromoles, even if the system is calling for light, you say threshold control. Don't provide supplemental lighting because the crops don't use more than this. Yeah, so it's money and quality as well. So that's a pretty cool setting that you can include. Night interruption is another way to control day length extension, right? Because day length extension, there is another way that short and long day crops, you can either give more light throughout the day or you can break the night time. That's the whole phytochrome response, which I'm not going to get into detail here. But if you want to use night interruption, and I don't know if this is an application for the citrus industry or not, if you want to do this, you can turn on your lights during the nighttime at minimum intensity. So it goes back, it's the same principle as the daylight extension. You turn on the light system, 10%, you break the night, and you don't waste too much energy. You can do zones, which is interesting. So if you have different applications in your greenhouse, you control all the settings in one part of the greenhouse for the lighting. And if you're doing a different application on the other side of the greenhouse, you have the option to have different controls and meet different criteria. This last one here, DLI carryover, this is something that was developed at University. Well, they did some examples, some studies, and they prove with lettuce. So I'm going to be very specific here. It doesn't work. I don't know if it works with every crop, but with lettuce, they found that the plants are they have plasticity, so they can adapt to variations. And they found that if one day you exceed your target DLI, and for lettuce is about 17 moles of light that they need per day. If one day you go 18 or 19 moles of light, they found that you can go 16 or 15 the next day. Kind of makes up for that. So they did a lot of studies. When I say DLI carryover, they are not carrying over the amount of flight. It's just that you got an extra one day, they work a little harder. The next day, they work a little less. And at the end of the month is smoothed out. And they have the same biomass production. So that was a pretty cool. This system that we use is no longer available. We start to play with that and provide savings as well. The principle here is, especially California again, if you get one day that is super sunny, you didn't pay any extra for the lights. Instead of having the 18 moles of light, let's say got you 20. So the system already automatic process this and change the target DLI for the next day to 16 because you got 2 more, 16. If you get extra light, great. If not, the whole calculation and supplemental lighting we provide up to 16, you save money again. But then you need a lot of studies this for the citrus, right? I'm not saying do this. I just say look into that. That could be something there. All right. With that, I conclude the presentation. I'll be happy to take any questions if you have anything. Thank you.
So we are going to take a couple questions. Yeah, question.
Just would like to know, I mean, there's a kind of trade-off because the lights should have some kind of life cycle for that. So turning it on and off, from decrease that. Or this is something that can start when
No, you're very right about this. You're very right about this. So with the LEDs, it's actually a good thing because with this system, we are dimming the LEDs. So you're not providing power. You're not power. The LEDs are power all the time. I'll try to be very basic on the. We can geek out later if you want. With the LEDs, you have a driver that takes the power from the outright, the AC power converts to DC, and that is what power the lights itself, the LEDs. So when you are using the dimming control, the power is always at the driver. It's just the gate of how much power you let to the LEDs itself. So you're going up and down, but the electronics, you're actually extending the life cycle.
you are not switching, you are kind of.
No, it's a 0 to 10 volts control, and that's all you let it go. The power, it's always power, and turning the driver on and off, that's where you go, you diminish the lifespan. So for the LEDs, is a good thing. Or the HPS is different. The HPS, because you cannot do that, you have to turn on and off the contactors. So now you call the ballast. That's the electronic that takes the power and power that it is. So in this case, you have to be careful because you might reduce. But normally with the LEDs, you change the bulbs way before the ballast. The bulbs go faster. For the HPS, there is something that I didn't mention here. There is a warm-up time on the bulb and on the ballast. So when you use adaptive lighting control for HPS, in our case, and I think most of the commercial companies do this, you build in a 30 minutes lockout window. So you turn on the lights, you cannot change anything within 30 minutes. It's the time to warm up and keep going. And the same thing when you turn off. You turn off, you have to be 30 minutes with the lights off before you turn on again. So the graph that I show for the LEDs going up and down, when you see the HPS are squares. It's all on or off. And sometimes you see exactly those windows because the weather is going like this, but you have to respect that. Does that answer the question? Oh, great.
I have a question. Is there a way when you do the adaptive lighting, the software and so on in the program to input that saturation point, the 600 micromole? Is there a way to?
In this system, yes.
All right.
But then as you talk to your climate control company, they probably do this. One thing to talk to the climate control companies, I think they're changing this now, but one I think was convenient before. They have weather stations. I think every greenhouse, probably your greenhouse here is the same thing. Sometimes the weather station is in a greenhouse up the valley, it's not that your greenhouse. What the weather station might be seeing might be nothing what your crops are seeing. So that's one important thing. I'm saying this because the threshold, they can, and that's how normally they turn lights on and off. But if they're making those decisions in a weather station that is far from your plants, it might be, you have to make sure, are you compensate for that? Or you ask them to upgrade with a light sensor inside of greenhouse. And then, yes, you can do that. You can do the side step.
Any other question? Right.
All right, thank you so
Thank
much.
you.